All right, so welcome to the 2.4 work example video. Again, our hope is that you watch the previous video to get some understanding of what the text was going to tell you about, went and read the text, or possibly read the text at the same time as watching the video. That is absolutely the best way to do it. And now that you've read the section and you understand continuity, we're coming back together and we're going to do an example together. So what we've done here is we've chosen a question that is not on the homework, but is extremely similar to one that is on the homework. And the question here is we're given a formula, we're given a function, it's defined piecewise. That square root symbol is a little bit annoying to me. There we go. So it says that for x, so notice this function is defined between 0 and 10, and between 0 and 3, it's defined as square root of kx. K is a constant. We do not know at this moment what it is. That's what we're actually going to find. And from 3 to 10, it's defined as x plus 1. So the question is, I didn't make f of x continuous at x equals 3. So what values of k make f of x continuous at x equals 3? And it may be that there are multiple, right? We're going to have to explain this. So this is wonderful. This is a perfect example to show what it means and remind ourselves what it means for a function to be continuous. So remember that f of x is continuous at 3 if these three numbers all exist and are equal. Okay, so we need these three numbers to all exist and be equal. And so what I want to do is one by one, just want to knock out what are they. So what is the limit as x approaches 3 minus of f of x? That means we're looking at x values. Remember, x approaches 3 minus means we're looking at values of x close to 3, but a little bit smaller. I have to ask myself, if I plug in an x value close to 3, but a little bit smaller, which of the two branches, that's what we call these, which of the two branches are we plugging into? Well, when you're less than or equal to 3, you go in this branch. So this portion of the graph, and this is key, and this is a fabulous way to write it, as long as you understand what's going on. If I'm plugging in values like 2.9, 2.99, 2.999, these values are getting very close to 3, but critically, they're all smaller than 3. So they're all being plugged into here. So the key is this is the same as the limit as x approaches 3 minus of square root kx. Now, square root of kx is a continuous function everywhere on its domain. So this has the ability, that's one of the powerful things about continuity. If you need to evaluate a limit with a continuous function, you can just plug in. That's actually one of the reasons why we love continuity. We have a ton of limits to evaluate, but limits with continuous functions, you can just plug in because by definition, the limit equals the function value. So what I was able to do is say, look, if you're only looking, we're going to draw a picture of this in just a minute. If you're only looking to the left of 3, if you're only looking at numbers less than 3, there is no difference between f of x and square root kx. But square root kx is continuous, so I can just plug in. So this becomes root 3k. Let's try the same thing. And you could even pause the video and try answering the next line yourself. I know that probably many of you are rolling your eyes, but you shouldn't be. That's a fabulous way to do this. So pause the video for a minute and try doing the next line and ask yourself, if I'm taking this limit, x approaches 3 plus, what am I plugging in? How does the function look? How can I solve this? And then the magic of pausing is that I don't need to stop. So I'm just going to give you a minute, pause the video. You should do this. I can play the Jeopardy music. I don't feel like humming it. Okay, so you're back. Congratulations. I appreciate the initiative. So if we're only plugging in numbers that are bigger than 3 into f of x, 3.1, 3.01, 3.001, 3.0001, numbers getting closer to 3, but critically they're all bigger than 3. Which of these two branches are we plugging them into? And we're only plugging them into this one. Any number bigger than 3 is going into here. And remember, the limit doesn't care what happens at 3. Continuity does. The limit doesn't care what happens at 3. Only cares what happens nearby to 3. So if we plug in these big numbers, this is going to be the same thing as if we were plugging them in to this function. This will always be what happens, by the way, with stepwise functions, with piecewise functions, excuse me, not stepwise, piecewise. This is always what's going to happen with piecewise defined functions. When you look at a limit near the point where the behavior changes, right, near the point where this change occurs, then you'll always be behaving like one function prior to that point and a different function after that point. It's just, that's what happens with a piecewise function. So here, because we're plugging in values that are of x that are close to 3 but bigger than 3, we're always plugging them into x plus 1. X plus 1 is a polynomial. We know it's continuous. So this limit is simply plugging in 3 into that function. Again, critically, I don't know that f of f is continuous yet, but I do know that each of these pieces are continuous because the text tells us so. So that's why I'm able to just plug in, but the best way to justify that is to say, look, when you're plugging in numbers less than 3, f of x looks exactly like this. But this function is continuous, so I can just plug in. Or when you're plugging in numbers bigger than 3, f of x looks exactly like this. But that function is continuous, so I can just plug in. Similarly, to figure out what f of 3 equals, we just have to look at which branch includes the less than or equal. Notice this one has the equal, this one does not. So we want to plug into the top branch, and we get root 3k. In order for the function to be continuous, I need all 3 of these numbers to be equal. Clearly, root 3k is equal to root 3k, so we're good there. But it, more importantly, has to equal 4. So square root of 3k. So in order to be continuous, we need square root of 3k to equal 4. And now I just solve for k. So k then, or 3k, let's do it this way, is equal to 16. And k is equal to 16/3. And this is my answer. This is the, in this case, unique value. There was only one. This is the unique value that makes this function continuous. Oops, wrong color. Oh well. makes this function continuous at x equals 4. Sorry, excuse me, at x equals 3. Apologies. All right. Hope that made sense. Talk to your instructor if it didn't. And thanks for watching this video.